In this lesson, we're going to look at stoichiometry and how we can go from the amount of one substance to the amount of another. This expands on what we did in the previous lesson, looking at just moles to include mass and other units. What we're doing now is called stoichiometry, and it is a quantitative study of reactants and products in a chemical reaction. What this allows us to do is to answer questions like how much hydrogen gas is produced when 1 kilogram of sodium metal reacts with water? How much iron is needed to produce 34.5 grams of iron oxide? These are just a couple of examples of the myriad of questions that we can answer using stoichiometry. We saw this diagram in the previous lesson, and we were focusing on the moles of A to moles of B using the coefficients from the balanced chemical equation. We're going to expand out a little bit and look at mass. So we're going to look at this region of the diagram. We can go from the mass of one substance to the moles, use the coefficients to go to moles of the other substance, and then back to mass. And as you can see, there are other ways to expand on this, and we're just going to focus on the mass to mass part at this point. We can describe this stepwise as the mole method because we're going through moles because that's where the relationship between two species exists. Not mass, not volume, but in moles. The first thing we do is write correct formulas for all reactants and products. So if you're not given a reaction, you might have to write out the reaction and then balance that resulting equation. Whatever value we're given, we need to use the tools we have to get that to moles of our known compound. Then we can use the coefficients from the balanced chemical equation to get the mole to mole ratio between the known substance and the unknown substance. Then we have moles of our unknown, and we can use our tools to get us to whatever we need to know for that substance. And then we want to ask ourselves, does our answer make sense? And this does take time. The more problems you do, the more practice you have, the easier it will get to decide, is this a reasonable value? Let's look at an example of how we do this. We have our balanced chemical equation. How many grams of CO2 are produced when 2.5 moles of O2 is consumed with sufficient C3H8? And we're given the molar mass of the CO2. Just like our problems involving moles or any of our dimensional analysis problems, we need to figure out what we know, what we're trying to find, and what relationships do we have. The first of which is our equation balanced? And in this case it is, but you should always check that the equation is balanced before you start the problem. Next, we look for our starting information. What are we given? In this case, it's 2.5 moles of O2, and we're trying to find how many grams of CO2. The sufficient C3H8 just means we have enough to react completely with all the oxygen we have. We're given the molar mass of 44.01 grams per mole for CO2, and we can also write a ratio, a mole to mole ratio between oxygen and carbon dioxide of 5 to 3. 5 moles of oxygen, 3 moles of CO2. We're going to start with our 2.5 moles of oxygen. That was our given value. That's our starting point. We know that moles needs to go on the bottom of the next step. Moles of oxygen specifically needs to go on the bottom of the next step. So we put in 5 moles of O2, and we can relate that with our mole to mole ratio to 3 moles of CO2. Moles of O2 are canceled. Now I have moles of CO2 in the numerator. I need moles of CO2 in the denominator in order to cancel out, and I can use my molar mass for this. I have 44.01 grams per mole of CO2. Moles of CO2 cancel out, and I'm left with units of grams of CO2. I do the calculation, and I get 66 grams of CO2. When we look back at this problem, we see we followed the pattern of we starting with moles of our known to moles of our unknown to grams of our unknown. The key thing to remember here is you have to go through moles, and you have to look at the mole to mole ratio from a balanced chemical equation. Let's look at another example with the same equation, which we know is already balanced. How many grams of H2O are produced when 10 grams of C3H8 is burned with excess oxygen? Again, we need to figure out what we're starting with, which is our 10 grams of propane or C3H8. We want to find out how many grams of water are produced. We have these two relationships, 2 molar masses, and we can also write a relationship from our balanced equation for the mole to mole ratio between C3H8 and water. We're going to start with our 10 grams of C3H8. I know that needs to be on the bottom of the next step. So we can put in our molar mass of C3H8 of 44.10 grams per mole of C3H8. Notice I had to invert that so that the grams were on the bottom, so those would cancel out. But my number, 44.10, stayed with the grams. Now grams will cancel out. And at this point, I have moles of propane in the numerator. So I'm going to have moles of propane in the denominator. And I put in the relationship there to 4 moles of water, 1 mole of propane. Now moles of propane cancel out. Now I need to put my moles of water in the denominator. And the relationship I know with water is the 18.02 grams per mole. And I put that into the next step. And moles of water will cancel out. This time, because I needed moles of water to cancel out, the moles went in the denominator for the molar mass, and the grams is on top. Now I have units of grams of water left, and when I do the calculation, I get 16.4 grams of H2O. In this problem, we added one little step of grams of our known to moles of our known to moles of our unknown to grams of our unknown. Again, using our mole to mole ratio from our balanced chemical equation. How many grams of nitric acid, and that's the formula HNO3, are produced from 100 grams of nitrogen dioxide reacting with excess water? The first thing we have to do is see if our equation is balanced. Looking just at the nitrogens, I can see I have 1 nitrogen on the left and 2 on the right. So I know my equation is not balanced. So that's the first thing I need to do. I'm going to figure out how many I have of each element. So I have 1 nitrogen and 2 on the right, 3 and 4 oxygen on the left and right, and 2 and 1 hydrogen on the left and right. Now I need to start putting in coefficients to balance my equation. I put a 2 in front of NO2, which changes the values of nitrogen and oxygen for the left, but I still don't have a balanced equation, but my nitrogens are now balanced. Next, I'm going to put a 2 in front of the HNO3 to balance the hydrogens, and we end up with 2 hydrogens and 3 nitrogens and 7 oxygens. Still not balanced. I change the coefficient for NO2 to a 3, and that gets me 3 nitrogens and 7 oxygens. Now we have a balanced chemical equation. Next, I need to look for what I'm starting with and what I'm trying to find. I see that 100 grams is my starting amount, and that's of nitrogen dioxide. And I'm trying to find out how many grams of nitric acid I'm producing. We have 2 relationships here with the molar mass, and we can also write a ratio between moles of NO2 and moles of HNO3 from the coefficients of our balanced chemical equation. Next, we're going to set up our problem starting with 100 grams of NO2. On the bottom of the next step, we need to have our grams of NO2, so grams per mole of NO2. I need grams on the bottom and moles on top so that the grams will cancel. Therefore, I have to invert the molar mass, and I invert the numbers as well as the units. With moles of NO2 in the numerator, I need moles of NO2 in the denominator. The relationship I know with that is 3 moles of NO2 to 2 moles of HNO3. Now moles of NO2 cancel out, and I've got moles of HNO3. Therefore, that needs to go in the denominator of the next step, and I can use the molar mass to get moles of HNO3 in the denominator, which leaves me with 63.01 grams in the numerator. Moles of HNO3 cancel out, and I'm left with units of grams of HNO3. I do the calculation, and I get 91.30 grams of HNO3. Notice, I set up the entire problem, make sure I was canceling out everything but the units I needed at the end before I actually did the calculation. Here, we went from grams of our known, which was the NO2, to moles of our known, to moles of the unknown, to grams of the unknown. Again, using the mole to mole ratio from our balanced chemical equation. How many grams of magnesium do we need to start with to produce 95 grams of magnesium nitride? First, we need to check that we have a balanced equation, which this one is not. So I need to figure out how many of each atom I have on each side. I see that my nitrogens are balanced, but my magnesiums are not. I need to put a 3 in front of magnesium, which gives me a balanced equation. Next, I need to identify what we're starting with and what we're ending with. And we're actually going to start with what we're producing, which can seem a little odd at first, but remember our starting point is just our known value. We can relate any two substances in a reaction regardless of whether we have two products, two reactants, or one product and one reactant. The moldable ratio can be written for any pair. This is our amount we're producing, but we're going to start our problem with that because that is our known value. Our end is the how many grams of magnesium we're trying to find. I can write a relationship for my balanced equation, 3 moles of magnesium to 1 mole of Mg3N2, but I'm also going to need molar masses because we have grams of the substances, we need to get to moles, otherwise we can't use our mole to mole ratio, and we cannot relate the two substances based on mass. So I find my magnesium has a molar mass of 24.31 grams per mole, and I just pulled that from the periodic table. For magnesium nitride, I need to calculate that value. So I have 3 times 24.31 plus 2 times 14.01, and I get 100.95 grams per mole for the molar mass of magnesium nitride. Now we can start our setup of our problem using our starting or our known value of 95 grams of magnesium nitride. I need to use the molar mass of magnesium nitride, putting the grams on the bottom. Therefore, 100.95 grams is in the denominator and moles of magnesium nitride is in the numerator. Grams of magnesium nitride cancel out. Now I can use my mole to mole ratio, which puts 1 mole of magnesium nitride in the denominator and 3 moles of magnesium in the numerator. Moles of magnesium nitride cancel. Now that I have moles of magnesium, I can use the molar mass to get back to grams of magnesium. 24.31 grams per mole of magnesium. Moles cancel out, and I'm left with units of grams of magnesium, which is what I'm looking for. And I do the math and get 68.6 grams of magnesium. Note that I'm still putting my substances in at every step, including the answer, as well as all of the relationships in the problem. We started with grams of known here. We went to moles of known, moles of our unknown, and then grams of our unknown. Going back to our diagram, what we see is that we were given a mass. We converted it to moles. We used the coefficients from our balanced chemical equation to get to moles of our other substance, our unknown, and then we could convert that to the mass using the molar mass. As we go along, we'll explore more of these pathways, but for now, we're looking at mass, moles, moles, mass, but always through the coefficients from the balanced chemical equation.